Hello everyone, this is the video lecture of section 12.1, calculus 3 to 2533. Okay, so this section 12.1 and 2 are supposed to be done by today. I'm a little bit late, sorry about that. There were some technical difficulties, but I think now I'm fine. So 12.1 and 12.2 I want you to do today, Friday, March 27th, and tomorrow, March 28th, Saturday. Okay? And then I'm going to send you an invitation to Zoom meeting on Zoom office hour meeting next Monday, 30th, March 30th. Okay? So before we do this one, let's go over definite integral. Definite integral was defined in an effort to get the area of the region under the graph y equals f of x and the x-axis if f of x is greater than equal to 0. So what we did was we split these intervals and x1, x2 all the way to xn. Okay, and then we choose x, delta x is b minus a over n, xi is a plus I times delta x, x1, x2, x3, and then choose sample point xi star from ith subinterval. So, for example, x1 here star, let's say this is x2 star, and this is, let's say, xi star. If it is xi minus 1, this is xi. And what we do here is we try to find the area of each rectangular column. Okay. Now the width of the rectangular columns are all delta x. The height will be determined from these y coordinate of these at these points corresponding to this xi star. So over here. Okay. So your area at the ith column would be delta x times the height. If you add them up, then you get some of the areas of the rectangles. So your area will be similar, so approximated by this f of x I star delta x. I think I'm going to use cooler. So that's the sum of the areas of the rectangle. Now that has some error. It's not going to be exactly the area of the region under the graph above the x-axis from x equals x equals b. But if we take the limit as n goes to infinity, that's going to be closer and closer to the area of the region. The limit value will be exactly the area of the region. So this is the way we define definite integral of a one variable function. Okay? Now, even if f of x is smaller than negative, that's fine. So for example, if you have this, then this definition, if you think about it, here that would be an area of the rectangular column. But I belongs to over here, your function value is negative of the height. So this will be negative of the area of the rectangle. So the first group of rectangles, this represent area of this rectangle, area of this rectangle, but negative of the area of this rectangle. So in this case, if this graph is y equals f of x, definite integral of f of x will be, if you call this area as A1, this one is A2, this one is A3, then that will be A1 minus A2 plus A3, right? Negative of the area of the region below the x-axis. So that was the concept of definite integral of one variable function. Now in this section we want to define definite integral of a two variable function on a rectangular region. So you can take a look at, I totally forgot. As usual, I uploaded all my lecture notes, the copy of my lecture notes of every section already in the course web page. Especially when you use video lecture, you have to have your copy of my lecture note, the copy of my lecture note on the table. Because I'm not going to write down everything you see on the lecture notes. At the same time, I'm going to write something you cannot see on the lecture note. It's the comments on some parts of the lecture notes. So you must have hard copy of your lecture notes so that you can write something on it. Or if you want, if you have some software, you can write on the PDF file, whatever. So you must have some form of a copy of lecture notes when you use this video lecture. So, and also obviously textbook, as always. Textbook page 831, figure 4 and 5. So, when you have a two variable function, imagine that you draw the graph of two variable function. Okay? Then, and your xy is in the rectangular region. This is between A and B, direct product C and D. What it means is collection of all point xy where x is on this rectangle, in this interval, y is in this interval. Okay? So the domain of this function will be this kind of rectangle. A, B, C, D. Okay? Now, so in the picture, you have, this is some curved something like this. So this is z equals f of xy. So this is coming from x-axis A and B, C and D. So this is the domain. X between A and B, Y between C and D, right? That one. X going this direction, Y going that direction. You're rotating around this, X moving this way, Y going this way. So what we do here is, the way we split the domain, in this case interval, into equal size subintervals, we divide
these rectangles using equal partition, uniform partition along x and y. Then you get this and this. So you partition along x and y, so you will have a subrectangle. Partition into equal size, uniform subrectangle partition. Alright? So you will have those partitions here. Alright? So use different color. And then different. And then think about the volume of the solid bounded above by this surface, the graph of f of xy, and the xy plane, and then side walls, right? Along here, side walls, front wall, side wall, back side wall, all right? So the walls are a cliff, vertical cliff. Your top is the surface from the graph of y equals, z equals f of x, y. So we want to find the solid, the volume of that solid. Now the way we do that is, we'll just want to find, think about this, one column. Think about the rectangular column rising from this little okay, rising. Okay. So it is a rectangular column. All right. So we want to approximate this volume of the solid using, think about it, chopping, cutting through this and cutting this way, and then you will have a thin rectangular columns, right? Rectangular column except for the top is part of the smooth surface, right? So we want to approximate the volume of each rectangular column, add them up. That will be approximation for the whole volume. So what we do here is, this is again x1, x2. Let's say this is xi minus 1, this is xi, this is xn. Let's say this is yj minus 1. So this will be ijth subrectangle, all right? And then you choose any point here, xij star, yij star, okay, that point. At that point, we find the function value and use that function value as the height of the rectangular column. So the volume of this ijth column, rectangular column, let's say delta Vij is approximately what? Delta x, this is delta x, which is b minus a over, they use m or n. M, this is m, this is y, n. Then delta y equals d minus c over n. This length divided by number of partition. Okay? So delta x and delta y, we call it delta a, the area of each subrectangle. Alright? So base area delta a times height. The top part is a smooth surface, but when you have a very thin, small, delta x and delta y, your top part is almost a little bit of, this can be approximated by function, the height, rectangular column. So this is a good approximation, height and base. Okay? So if you add them up, your volume will be approximated by delta Vij. That is f of xij star r. Here in this case, you have to do summation. J runs from 1 through n, I runs from 1 through n, right? For given I equals 1, J runs from 1 through n. For I equals 2, J runs from 1 through n. So you have a double summation. That is V. So I from 1 through n, J. So f of x ij star, y ij star, delta x. The volume of each ijth rectangular column, summation, that's an approximation, obviously. But, just like this case, the smaller this sub-rectangles become, the better the approximation, right? Delta is getting smaller and smaller means n goes to infinity. Delta y going to 0 when n goes to infinity. So, your true value, the limit, as m and both going to infinity, where this double summation this is delta A. Okay? Limit of double Riemann sum. We call it double Riemann sum. Of f. This is what we call double integral of function f of xy on that rectangular region R. Okay? So, if you compare with the definite integral of one variable function and double integral of the two variable function, it's the same concept. Just for one dimension or two dimension case. Area versus volume. Now, even though I just implicitly assume that your f of xy is positive, so that it is above the xy plane. In this setting, f can be negative. Just like, sometimes your f of x is negative. Then your volume will be, your definition will be the sum of the volumes of the region above the xy plane minus sum of the volumes of the region below the xy plane. Just like that. Okay? Alright. Now, because of the limit properties, you have the following properties. Okay, I'm not going to write it, so I'm going to just read it. So take a look at the bottom of page 1. What do you see? Double integral of f of xy plus g of xy is double integral of f of xy plus double integral of g of xy. So, okay, I'm going to write it. Just like a one variable case. By the way, this one is if the limit exists. If the limit exists. Then that limit value is called double integral. In that case, we say function f is integrable when the double integral exists. Now, let's assume that f and g are both integrable function. Then the sum of the two functions also integral function. and whose value will be just sum of the each double integral. That means your definite double integral operator, double integral can be split over addition, and any constant multiple of the integral function is integral. So this is also well defined, and that value is same as c times double integral of f. So constant multiple can be taken out of it. These two together is called linear properties of definite integral, in this case double integral. And third property is if f of xy is greater than or equal to g of xy. For all xy in this rectangular region R, then double integral of larger functions is greater than or equal to double integral of a smaller function. These are all, you have exactly the same properties for definite integral, right? Now, our example 1 is example 1 on your textbook, page 833. So, page 833. Now, estimate the volume of the solid that lies above the rectangle. R is 0,2 by 0,2. And below the elliptic paraboloid, okay, z equals 16 minus x squared minus 2y squared. Okay? Divide R into 4 equal squares and choose the sample point to be upper right corner of each square. Sketch the solid and the approximating rectangular boxes. It is very hard to draw, so I'm going to just refer to the picture of the textbook. You see that? They draw. So 4, they say that 4 equal squares. Your domain is from 0 to 2. 0 to 2. In order to have 4 squares, you have to divide into 2 and 2 along x and y. Okay? So in this case, both m and n are 2 case. 2 and 2. Delta x equals 1, delta y equals 1. So delta a equals 1 times 1, so 1 unit square. Alright, so then the Riemann sum. They want you to choose xij star, yij star as what? Upper right corner. So for the first one, they want you to choose this one, upper right corner here. I'm going to write slightly inside, even though it is exactly on the corner. For this rectangle, we have to use this one as a sample point to calculate the value. So, in that case, Riemann sum volume will be approximated by, what is it? From 1, 1. This is so-called 1, 1, the first. So, base area times function value at 1, 1. That will be this. Alright? First one. Second one, the volume of from the second one is on that region. Base area times function value at 2, 1. And we use your function value is 16 minus what? 16 minus x squared minus 2y squared. Okay? There's an elliptic parabola starting from 0, 16 going down like this. Okay? The cross section of sheet is ellipse. And then third one will be delta A f of, what is it, 1, 2. Finally, delta A times height f of 2, 4, 3. Now, delta A is just 1. Everything is 1, right? So, you just have to calculate f of 1, 1. What is f of 1, 1? Plug it in. 1, 1 minus 3, 13. 2, 1. 4 minus, so 10. 1, 2. 2, 8 minus 9, so 7. 2, 2. 8, 4, 12, plus 4. Add them up. 11, 21, 34. Okay? So you're going to get 34 as the approximate value of the volume, right? This is a Riemann sum when you have n equals 2, n equals 2, and choosing upper right corner. Okay? Now, in our notes, do the same problem, choosing the sample point to be the lower left corner. So instead of these 4 points, we're going to use not this one for this, and this, and this, right? So in that case, we'll have to use f of 0, 0. Here, f of 1, 0. Here, f of 0, 1, f of 1, 1. Okay? So that would be approximate value using lower left corner. And if you do that, you'll find that that one will be, if you calculate it, 58. Okay? Finally, C will be when you use the middle point. So f of point 1/2 and 1/2, right? 1/2, 1/2 for this. No, delta base area is always 1, so I don't have to worry about it. And then for this one, f of 3 over 2, 1/2. This one, f of 1/2, 3 over 2. F of 3 over 2, 3 over 2, right? 1/2, 3 over 2. And if you calculate this, you will get 49. Okay? So this, we can call this one a midpoint rule, just like the definite integral, one-dimensional case. Now later, note that we will calculate exact value. That is actually 48. Look at this. It is quite close, isn't it? Just a little over 2% error. Even though you have a very crude approximation, just using two splits, right? Because when you use midpoint rule has a pretty good approximation. Okay. All right. Now we learned that if f of xy is positive, then double integral give you geometrical meaning. That is volume of a solid, which is under the graph of f of xy, above the xy plane, z equals 0, and these walls. Above, rectangle, a to b, c to d, right? So using that, let's do the following example. That is example 2. Evaluate this where r is 0, 3 by minus 2 and 2. So x runs 0 to 3, y runs minus 2 and 2. This is really hard to redraw. Okay. Okay, well, let me do my best. Okay, this is 2 and negative 2 over there. Y runs from negative 2 and 2. X runs from 0 to 3. Now, this is the graph of z equals 4 minus y squared. Now, this is function of x and y. It's just a special case where x does not show up. Now, what kind of graph is this? If you square both sides, you get, on the YZ plane, that would be upper semicircle, right? This is a circle equation, but this one is positive square root. So z is greater than or equal to 0. So minus 2 and 2. Good, that one. Okay? Now, as a xy equation, your x-axis is going like this. So your graph will be like this. What is it? Like a greenhouse, top of a greenhouse. That would be the surface of this graph, right? Projection onto the YZ plane is upper semicircle, but it doesn't depend on x. So every point, here, and then parallel to the x-axis everywhere, parallel to the x-axis, parallel to the x-axis. That'll form circular dome, right? Greenhouse. From minus 2 and 2, 0 to 3. Your graph is above the xy plane on that region, right? So this must be above. So if I call this one as I is the volume of the solid. What kind of solid is this? Semicircle extent. That's half of a cylinder, isn't it? Right? This is half the cylinder. Half cylinder. So half cylinder means 1/2 times base area times height. Your base area is a half. Okay. Half times pi r squared h, right? This is cylinder area, that's volume of the cylinder. The cylinder radius is 2. Height is 3, right? So it's 6 pi. So that will be exactly 6 pi.
Now, recall, when your function is changing like this, how can we define average value of a function on that interval from a to b? And we define average value this way. Definite integral of a b f of x dx times 1 over b minus. Right? The whole area divided by base length. That means average height. Right? So this value will give you average height. When you use that average height as a height, then rectangular area will be exactly the same as the area of the region. Anyway, that's the way we define average value of a function on an interval. Likewise, average value of a function on a rectangle R would be, alright? So, if some function defined on this interval R, then average value on that rectangular region will be 1 over the area of the rectangle. Double integral of that function on that region. Same concept, right? Definite integral over length. Double integral divided by total area of the region. They will give you average value of the function over the region. And that average value has a lot of practical concepts. And very interesting example is, our example 3 is example 4 on your textbook. Our example 3, 4, on page 835. Oh, by the way, let me check whether this video recording is going well. Okay. So, here, we want to find average snowfall. Average snowfall over the, they say this is Colorado. They approximate Colorado as some rectangular region. Alright? So f of xy should be, the snowfall. The snowfall in inches, okay, on certain date in Colorado at xy, okay. Then average snowfall in Colorado, in the state of Colorado. How do we find average snowfall? Certain region, mountainous region, there's much deeper, bigger snow, and much more snow, and then some regions much less snow. How are we going to average out? Well, using this. You just have to find double integral of a snowfall function and divide by the area of the region. But of course, there's no nice formula for this as a function of x and y. You only have some data, scattered data. They gave you this f of xy using contour method, right? So, here, this value will be average snowfall. That is, area of the region, the rectangular region, times double integral of this. But we don't have a formula, we don't know how to calculate this, but we can approximate this one by using double Riemann sum. Here in this case, we decided to use, and then this one is j from 1 to 4, f of xi bar, yj bar, delta a.
So this is midpoint rule. We're going to choose in each right. Along x, we split into 4. Along y, also split into 4. Totally 16 rectangles. All right. Then total area, if you use calculator here, they gave you 388 miles times 276 miles. This times this square mile. All right. And then delta A is just this area of R over 16, isn't it? Okay? So, what do you get? 1 over R. So this average value will be double Riemann sum over 16. So these cancel. So what you have here is 1 over 16 times this double Riemann sum, that is f of x1 bar, y1 bar, f of x1 bar, y2 bar. So you have to calculate function value at the midpoints from all these rectangles, right? So if you take a look at textbook, you see, page 836, all right? They put these midpoints on each of those 16 subrectangles, right? And they calculate function value over there. The very first one, lower left corner, there, well, if you look at the contour map, it is, 0. Now, to the right, your midpoint is almost 16, but slightly less, right? So we can calculate, that's about 15. And the next one, about 8, right? I'm going here, bottom, and then this, and then this, and then this. Okay. 8. The next one, 7. And then the second layer, that is about between 0 and 4. So it looks like 2, right? So I'm doing this way. Just counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm going to count. So 2, and then 25. Look at that. Yeah, very close to 24, but slightly larger. So I put 25. About 18.5, 11, 4.5. And so forth. You just take a look at textbook. And then that value will be about 12.9. So about 13 inches. Okay? So we use this concept of average value of two-variable function on a rectangular region as double integral of that function divided by the area of the region. But because we don't know how to get double integral exactly, we use double Riemann sum as an approximate value. And here we divide it 4 by 4. So 16 subrectangles. Okay? Alright. That's the end of 12.1. Now I will upload 12.2, section 12.2 lecture by tomorrow, sometime tomorrow, so that you can, these are very simple, easy sections, so you can go through the homework problems easily. Okay, so I'm gonna send you a Zoom invitation. So if you have any question during that Zoom meeting time, you can come on and ask any questions to me. I'm gonna be in front of my computer
because I have three different courses, I have to have 3 separate meetings. So I'm going to set aside probably 1 hour next Monday around your original class time. Not exactly same, but around that time. Okay? I'm going to send you a Zoom link to that Zoom meeting. So you're supposed to ask questions from those 2 sections, 12.1 and 12.2, just like our usual lecture case. And then you're supposed to finish those ones by Thursday. Okay? Also by Monday, I'm going to upload lecture videos 12.3 and 4. And you have to try those homework plans by Thursday. And Thursday, we're going to have some Zoom meeting. Office hour. Basically, it's office hour. So I'm going to let you know my schedule throughout till the end of the semester, so that you will know which sections cover when. So then you have to know, you have to keep up the pace, right? When you have online sessions, keeping the pace, keep up the pace is the most important thing. All right? So more details will come. All right? And sorry for the late upload. There was some technical difficulties, some problems, but I think I resolved it. So this is the section 12.1, and section 12.2 lecture video will be uploaded tomorrow, Saturday, March 28th. Okay? And those 2 sections are the ones you have to study by the end of the weekend. And then bring some questions Monday, Zoom meeting, Zoom office hour. Okay? All right. Thank you. See you next time.